Okay, so welcome back. This is the third video about probability calculus, and in this video we're going to discuss the concept of independence and conditional independence. These two topics will be of central importance for us to understand the Bayesian networks and other probability graphical models. So let's start with independence. So we haven't seen a little bit of these in the previous video, when we computed the probability of earthquake, and we saw that the probability of earthquake was the same of the probability of earthquake given burglary. Both of them were 0.1. So the probability of earthquake did not change when we observed a burglary. So these two events are independent of each other. And we can say that an event alpha is independent of an event beta if and only if the probability of alpha given beta is equal to the probability of alpha, or the probability of beta is equal to 0. So what's happening here is that as the events are independent, when I observe one event and I call it beta, it doesn't change the probability of the first event, call it alpha. We also found the opposite, right? We found that burglary was independent of earthquake because we computed the probability of burglary and it was 0.2. And we computed the probability of burglary given earthquake and it was also 0.2. And it did not happen by chance because this is a general property. If an event alpha is independent of an event beta, then beta is also independent of alpha. And we write it like this. Alpha is independent of beta, and beta is independent of alpha. You see my slides that I frequently use the symbol like this, that simpler version of the original and the most appropriate symbol for independence. It is because the software that I use to make the slides do not include the most complete symbol. So we find that a probability P finds alpha and beta independent if and only if the joint probability of alpha and beta will be equal to the probability of alpha times the probability of beta. And people usually take this as definition of independence and take this first property here as a consequence. But we can obtain one from the other, right? So if you think that the probability of alpha given beta is equal to the probability of alpha and beta divided by the probability of beta, right? And if these two events are independent, so we can take this property here, and you're going to write that the probability of alpha given beta is going to be equal to the probability of alpha times the probability of beta divided by the probability of beta. And we can cancel out these two, so the probability of alpha given beta is equal to the probability of alpha. So we are just showing that this property is true if we have this definition of independence. And we can show also the other way around. Okay, many people think that independence and mutual exclusiveness are the same notion, but they are not. As we just saw, the probability of alpha and beta, if these two events are independent, is equal to the probability of alpha times the probability of beta, right? And it's very different what happens with the mutual exclusiveness. When two events are mutually exclusive, the joint probability of the two events is equal to 0, because if they are mutually exclusive, we have alpha here and beta here, but there is not a single world where the two events they hold at the same time. So the intersection here is going to be 0, and when you compute the probability, there will be no worlds that you can sum the probability of the worlds in order to make this joint probability here. So we say that these two events do not hold, sorry, here there is a type, do not hold together at a same world, so the joint probability of them is 0. So most of the time we think about independence as static notion, but actually it is dynamic. So if you have two events that are independent, they may become dependent if we give another piece of information. At the same time, if two events are dependent, we can make them independent, providing some extra information too. So it's just to give you one example. We saw a few slides ago that burglary was independent of earthquake. So we saw that the probability of burglary was equal to 0.2, and we saw also that the probability of burglary given earthquake was also equal to 0.2. So burglary and earthquake are independent of each other. But we also saw that when we add information about the alarm, we can tie these two pieces of information together and make it then dependent. So we saw that when we have probability of burglary given an alarm, it was 0.741. But when we came out with the probability of burglary given an alarm and earthquake, it lowered down. So we were saying that burglary and earthquake that we have here were independent, but with the information of alarm, they become dependent. And that is very interesting. And that's happening because burglary is an explanation for alarm. So when we see an alarm, the probability of a burglary increases. It was originally 0.2 and it goes to 0.741. But when I say that I had an alarm and an earthquake, the earthquake becomes the explanation for the alarm activating. So the probability of burglary given alarm and earthquake decreases and goes back to 0.253. That's almost the same that I had before, that was 0.2. So burglary and earthquake that were independent, when we saw here, became dependent when we added information about alarm. And this may sound a little bit strange in the beginning because we tend to think about independence as a static concept, as a static notion, but it actually is not. So another example is like you have two dice and you're going to throw them, and we have to agree that the outcome of one die will not influence in the second die. So that will be independent events, the outcome of the first die and the outcome of the second die. But if we give a third piece of information that is the sum of the outcomes, so now this information become dependent, right? If I tell you that the sum of the numbers of the two dice is 10, if you know what is the outcome of the first die, you will figure out what is the outcome of the second die. So we can make events that are independent, dependent, and something that are dependent, independent by adding more information. So let's look at another example. So here we have this table when we have all possible worlds. We have three binary variables, temp, sensor 1 and sensor 2, and the values can be normal or extreme. And let's switch slides here. And those sensors are a little bit noisy, so they will not always read the same thing. But let's compute some initial probabilities. So the probability of temperature being normal is 0.8. The probability of sensor 1 being normal, 0.76. And the probability of sensor 2 being normal, 0.68. So they are not exactly the same, but they are some way correlated. So we can imagine that these two sensors are somewhere, I don't know, maybe close by in the same room or something like this. So if I know the reading of one sensor, that will change the probability of reading another sensor. So those two sensors are not independent from each other. So we can check that, right? So we compute the probability of sensor 2 being normal, given that sensor 1 is normal, and that increases to 0.768. So it was 0.68, now increase it to 0.768. So it's a small increase, but there is a change here, right? So knowing one sensor will change my belief in the other sensor. And that makes sense if the sensors are some way close by, maybe in the same area. So let's now look at one different setting here. Let's suppose that now I know the temperature, and the temperature is normal. Okay, so the reading of sensor 2 being normal will be 0.8. So it increased from here. It was 0.76. Now I know the temperature is normal. It increased a little bit. It went to 0.8. But if we add another piece of information, that is the reading of sensor 1. So we saw here that sensor 2 was not independent from sensor 1. Reading sensor 1 first would change our beliefs in sensor 2, but now that we know that the temperature is normal, look what is happening here. The probability of sensor 2 being normal continues to be 0.8. It didn't change anything. So the explanation here is that temperature being normal is around enough information for us to figure out the probability of sensor 2 being normal. And sensor 1 being normal, this extra information, does not change our belief, does not add value to what we already knew. So it continues to be 0.8. So we say that sensor 2 is not independent of sensor 1. So we have sensor 1 and sensor 2. They are not independent from each other, right? But if I know the temperature, they become independent of each other. We say that sensor 1 is conditionally independent of sensor 2. So sensor 1 is not independent of sensor 2, but sensor 1 is conditionally independent of sensor 2 given temperature. So if I know temperature, these two events become independent of each other. So as we said, right, so in general, if we have two independent events, they can become dependent if we have some new evidence. And if at the same time, if we have two dependent events, they may become independent if we have also some new evidence. So let's look at what is the definition of conditionally independent events. So an event alpha is conditionally independent of an event beta given an event gamma if and only if we have this property here. The probability of alpha given beta and gamma is equal to the probability of alpha and gamma, or the probability of gamma is 0. So a way of trying to remind this property is like saying, okay, beta is not adding new information to us, so we can remove it and the probability will stay the same. So the information that gamma provides to us is enough to figure out what's going to be the probability of alpha. And beta does not add enough information to change that probability. So as we saw with independence, conditional independence is also symmetric. So if alpha is conditionally independent of beta given gamma, if and only if beta is conditionally independent of alpha given gamma. So we say that if alpha is conditionally independent of beta given gamma, it's also true that beta is going to be conditionally independent of alpha given gamma. So it's a symmetric relationship. So although this first equation here can also be taken as a definition of conditional independence, most people understand that this second equation here is the definition and take the first one as a consequence. So here we say that alpha and beta are conditionally independent of each other given gamma if the probability of alpha and beta given gamma is equal to the probability of alpha given gamma times the probability of beta given gamma. So it's very similar to the definition of independence that we saw before, but now both events are conditioned to gamma, or the probability of gamma is equal to 0. And of course, we can prove one definition, one property from the other one, right? So, for instance, we can start with the probability of alpha given beta and gamma, and that's going to be equal to the probability of alpha and beta given gamma divided by the probability of beta given gamma, right? But if we take the definition here, or at least the second definition, that's going to be equal to the probability of alpha given gamma times the probability of beta given gamma divided by the probability of beta given gamma, right? And we can cancel these, and we have that this is the probability of alpha given gamma. So exactly what we have here in this first equation here. So we can extend this notion of independence that we have for events to variables. So if we have three variables, x, y, and z, and we want to say that x is independent of y given z, what we have to show is that for every possible instantiation, I will call little x, little y, and little z, for every possible instantiation, we have that the event x is independent of y given the event z. So if that holds for every possible instantiation, so the variables will be independent or conditionally dependent. So we can understand that this concept, this notion of independence and conditional independence is stronger for variables than it is for events. And we can also take one step further and talk about independence of sets of variables. So we mind from our notation that if we use capital bold letters, we are talking about a set of variables. And imagine that we have three disjoint set of variables, x, y, and z, so they do not share any variable in common. And we want to say that x, the set x, is independent of the set of variables y given the set of variables z. So what we need to show is that every possible instantiation, little x, notice again that I'm using little x with a bold face because that's going to be a set of values of variables. So it's going to be all instantiations for the variables x that belong to this set here. So these instantiations little x will be independent of the instantiations little y given little z for all possible combinations, right? So we denote it like this. The set x is independent of y given z, or we can also write it like this way. It's also very common. You will find it in some books. So this I here, it stands for independence. The P is representing the probability distribution where this set of variables are conditionally independent. And we look here, we have x, z, and y. So we can interpret it like this, that z in the middle here is making x independent of y. So just to make it a little bit more concrete, let's suppose that x is a set of variables a and b, y is the set if you have just one variable c, and z is the set that has the variables d and e. So when we state that x is independent of y given z, you are saying actually that a and b is independent of c given d and e. And we take another possible value here. We assume that these variables are binary. So we're going to take that a and not b is independent of c given d and e. And we take another possible combination that is not a and not b. is independent of C given D and E, and we try all possible combinations. So we have to confirm for all possible instantiations that these conditional independence are true. We will end with not A and not B is independent of not C given not D and not E. So in total, this statement here is the same as saying that we have 32 independence statements, because we have 32 possible values given that we have 5 binary variables. So a very interesting concept is mutual information. So we can understand the independence as sort of a special case of mutual information. We can say that mutual information in some way quantifies the impact of observing one variable in another variable, in the uncertainty of another variable. So it's a very useful measure for dependency between variables. And the definition is this one. And we can see that for some events, so we are taking the mutual information between two variables. We're going to sum for all possible instantiations of x, y, and multiply the probability of x and y by log in the base 2 of the ratio of the probability of x and y divided by the probability of x times probability of y. And of course, for some events, x and y, we may have 0 probabilities, but in this case, we're going to assume that 0 log in the base 2 of 0 is going to be equal to 0. So we can still compute the mutual information in the case that we have some events with 0 probability. But what I find interesting in this ratio here is the fact that in some way it measures the dependence between two variables in a full spectrum of values. So we can think of P, the ratio P of x and y divided by P of x times P of y. So at the really bottom here we have the value 0. And if we assume that P of x and P of y are not 0, so what you cause this ratio to be 0 is that P of x and y is 0. And that's going to happen when we have mutually exclusive events. So you can think that on the really bottom we have mutually exclusive events, and we can go up and go and approach the value 1. The value 1 is going to happen when we have P of x and y equals to P of x times P of y. That is the definition of independence. And as this ratio increases, what's going on is that the dependence between the two variables are increasing too, because we have the joint probability of x and y being larger and larger, meaning that these two variables tend to occur together very often. So in some way we are measuring the dependency between these two variables x and y by looking at a full spectrum of possible values, from mutually exclusive events, going through independence, going through to something that is a more stronger dependence. So of course this ratio, we're going to pass through this log function. So you should remember that the log function has a shape has a shape like this. So it will never touch the y-axis, and when it crosses the x-axis, it's going to be 1 here. So when this ratio is 0, this log function will convert that to 1. So if you have two independent variables, the mutual information of x and y will be equal to 0. Something that is a little bit more complicated to see is that the mutual information between two variables will never be a negative value, right? And we can see from these two equations here that the mutual information of x and y will be equal to the entropy of x minus the conditional entropy of x given y, right? And we know that the conditional entropy of x given y is less than or equal to the entropy of x. So actually it's showing that this property here, that's a non-negative value, should be true. And we can also define it the other way around. So we can also understand the mutual information of x and y to be the entropy of y minus the conditional entropy of y given x. Okay, we can take one step further and define a conditional mutual information. So the conditional mutual information will be very similar to the mutual information, but we're now conditioning the probabilities to a third variable, z. And as we saw that the mutual information can be understood as a difference between entropy and conditional entropy, this also happens here. And we can extend the notions of entropy and mutual information to sets of variables as it's expressed here. So, okay, we get to the end of our third lecture. So we discussed some fundamental aspects of probability calculus. So we discussed how we can update beliefs and what is independence and conditional independence. We should take a look at the third chapter of our textbook with a section of section 3.6 and 3.7. There are still three topics that I want to cover, but they're going to move that to the next lecture. One is chain rule. The other one is the case analysis, also known as the law of total probability. And the third one is the Bayes rule or the Bayes theorem. So these are three very important notions that we need to discuss with more detail, but I'm going to push these to the next lecture. So see you soon.